Okay, thank you very much for inviting me. I'm really grateful for quite a few of the previous speakers who created a perfect setup for my talk so that I can avoid giving some definitions that I usually have to give. So basically, this talk can be viewed as built up on one remark of Bruno. He said that operads, results on operads can be guessed and then proved based on thinking about respective results for associative algebras. And what I will do, I will begin with giving one alternative definition of an operad equivalent to the one Bruno gave, which will sort of enforce that philosophy and allow us to view operads as monoids in a certain monoidal category. And then it will be the turn of another remark from the previous days to pop up, namely Ike mentioned that when we deal with symmetric operads, symmetries tend to cause a lot of trouble, and so I will explain what exactly you cannot borrow directly from associative algebras when dealing with symmetric operads. And then on the bright side, I will explain how to defeat that problem by moving to a slightly different monoidal category and monoids there, extending the notion of an operad a little bit, and actually be able to apply various lovely techniques from associative algebras, and that would be partly related to some remarks of George Barnatan, but we'll see how it goes later. So let me. I was very pleased during this conference by noticing that people from the operad side tend to use the words category and functor much less than people dealing with multiple zeta values. But I will unfortunately sort of shorten this gap and start in the very beginning by defining a few categories to give that definition of an operad that I really like. So these definitions are now fairly standard. So let me, though, begin with one disclaimer. When I will be talking about operads throughout this talk, I consider operads concentrated in positive arities. I do not allow constants in respective algebraic theories. So operads without elements of arity 0, or so if you just look at the definition that Bruno gave, you should just assume in that definition that natural numbers do not contain 0. So by fin, I denote the category whose objects are finite sets and morphisms are bijections. Sorry? That's right, non-empty finite sets. And by ord, I denote the category whose objects are non-empty finite ordered sets and morphisms are order-preserving bijections. So an incredibly rigid category between any two objects. There are either no morphisms at all or precisely one morphism.
When you say ordered, you mean linearly?
Linearly ordered, yes. And the two categories built out of these, which are intimately related to the two versions of operads that Bruno defined, symmetric operads and non-symmetric operads, are categories of functors from these two vector spaces. So the category of symmetric collections is the category of functors from fin to vector spaces, and the category of non-symmetric collections is the category of functors from ord to vector spaces. In fact, yeah, it should be contravariant functors. So and somehow this is already very much, you can see how it is related to the sort of data that Bruno needed when he defined operads, because to define a non-symmetric operad, we need a collection of vector spaces P of n for each n. And to define a symmetric operad, Bruno needed a collection of P of n, where for each n, P of n would be a representation of the symmetric group Sn. So, of course, to define such a functor, it is enough to define it on some on your favorite finite set for each given cardinality, and then extend it by functoriality. So to define such a functor P. By P of n, I just define P applied to integers from 1 to n, which you can view as a finite set or a finite ordered set with a standard order, so in both cases. But it is important that in the first case, in the case of symmetric collections, finite sets have their symmetries. So each P of n would be automatically the representation of the respective symmetric group because of functoriality. Automorphisms of finite sets act on their images under respective functors. And now I'm going to remind you that these categories, the category of symmetric collections, the category of non-symmetric collections, both have structures of monoidal categories, and then the corresponding two versions of operads, symmetric operads and non-symmetric operads, will be just monoids in those monoidal categories. So, let me do it on two sides of the blackboard for symmetric and non-symmetric case. So in the symmetric case, suppose that we have two symmetric collections P and Q. Their composition, to define their composition, I need to teach you how to evaluate it on any finite set I. So P circle Q of I is going to be the direct sum over all k starting from 1. Okay, let me just write it down and then explain. So I take the direct sum over all k starting from 1, p applied to integers from 1 to k, tensor over the symmetric group with this big direct sum over all surjections from I to integers from 1 to k, q applied to the pre-images of integers from 1 to k and this surjection. And the symmetric group sk acts on this direct sum by permuting elements in the target and acts on this because it's the, as I said, it's symmetries of integers from 1 to k, so p applied to integers from 1 to k is a representation of sk. And somehow, if you view for each finite set I, the vector space P of I, as the set of all operations of type P whose inputs are integers, inputs belong to the set I, then this formula just precisely explains you how to do the two-level tree compositions that Bruno was talking about. So you take one operation of type P, whose inputs are labeled by integers from 1 to k. You take k operations of type Q, you plug them in here, and then to let this operation have inputs from the finite set I, you need to distribute I between the inputs here. And such a distribution, of course, defines you a surjection from I to integers from 1 to k. And tensoring over the symmetric group means just reasonable equivariance. If you simultaneously permute the inputs of this operation on the bottom and the operations that you plug in, you should, of course, get the same. So this is what is happening. And in the non-symmetric case, it is very similar. So you write the same formula with two exceptions, with two differences. You remove the symmetric group because tensoring over the symmetric group doesn't really make sense anymore. A symmetric group doesn't act on the left. And you restrict yourselves to surjections which are non-decreasing. So this and this essentially means that in such a composition, two-level composition, the inputs will always be in the same order, so you can safely suppress them, and that's what Bruno was doing in the beginning when, for example, discussing the associative operad, because in the associative product, in the relation of associativity, arguments are in the same order, so we can just suppress them. Okay, so that's and now a symmetric. So the properties of these of these circles are that they do indeed define on the respective categories of functors the structures of monoidal categories. For the unit, you just take the collection which vanishes everywhere except for one-element sets, and in one-element sets is a one-dimensional vector space of the ground field. And the asymmetric operad is a monoid in the first category, a non-symmetric operad is monoid in the second category. Now, we've fully made sense of that remark of Bruno, that we can think of, we can apply our intuition of working with associative algebras and deal with operads as associative algebras. When we work with associative algebras, say, defined by generators and relations, as it often happens with associative algebras, and as you saw, it often happens with operads too. For instance, the associative operad, Bruno wrote that presentation with generators and relations. Then it is, well, we often want to compute something and to see what are the basis elements, how to actually compose those basis elements, and so on. For algebras, one very good strategy is to take an algebra with some generators and relations and then sort of degenerate it into something much simpler, degenerate it into an algebra with just monomial relations, whose relations say that some monomials are equal to 0. So for instance, I can write you, let me say, 3 different algebras here. Both have generators x and y, and one has relations xy minus yx equal to 1. It's the algebra of polynomial differential operators on the line. Another one the algebra with relations xy equal to yx, the algebra of polynomials in 2 variables. And finally, the algebra with generators x and y and the only relation xy equal to 0. As associative algebras, these 3, of course, are very different. However, the monomials y to the power a, x to the power b form a basis in each of these algebras. So somehow for the third algebra, it is painfully obvious because monomials where xy appears vanish and other monomials are evidently non-zero and linearly independent. For the second algebra, it is of course very standard because we know what polynomials in 2 variables are. For the first algebra, well, you need to check something, but it also is an easy exercise that these elements form bases. So somehow the first algebra is filtered, and the corresponding graded object is the second algebra. Unlike the setup of drawer's talk, here the corresponding graded object is not isomorphic to the original filtered one, but at least it is definitely isomorphic as a vector space, so we can at least capture the basis. But what I suggest is to view even the second algebra as a filtered one. Namely, we should view in this relation, we can say that the monomial xy is more important than the monomial yx. And then moving to a corresponding graded object using filtration defined by linear ordering of all monomials, we kill this lower term and move to the algebra number 3. So we have, and we get an algebra with just monomial relations. And this, so this idea is for people who deal a lot with algebras defined by generators and relations, has many different names. People use words like Grobner basis, diamond lemma, and so on. But the idea is that in the associative case, for any algebra presented by generators and relations, you can find, if you just drop everything in the relation except for the leading terms and consider the algebra whose relations are leading terms of relations, you might be in trouble. The corresponding algebra with whose relations are leading terms might end up being bigger. But the statement is that it's always possible to find a good set of relations for which, if you retain the leading terms of them, you will get an algebra with, of the same size, with the same basis. And that is a very nice thing in general, because at least it is very, as you see, it is very easy to describe a basis when all relations are monomials. But it is much easier to do other things. It is easy to answer some questions of homological and homotopical algebra. I'll try to say a little bit in my talk, and if I don't have time, then you will see it in exercises for Bruno's course, I'm sure. Now, let me explain you how exactly symmetries get in the way, why we get in trouble when we try to adapt this idea to the case of operads. Okay, it's not very difficult to adapt it for the case of the associative operad because it is non-symmetric. For non-symmetric operads, life is, well, non-symmetric operads have no symmetries, so there is nothing to get in our way. The simplest example of a symmetric operad where you can see those troubles is one of the simplest examples of operads at all, is the operad controlling Lie algebras. Fortunately, from Ike's talk yesterday, you already have a good intuition of what a free operad is. So in Ike's talk, operads were non-symmetric, but okay, in the symmetric case, you just start from a symmetric collection and start building trees decorated by elements of that symmetric collection. Of course, so the operad Lie is the free operad on one binary generator, and since our generators are symmetric collections, to define a generator, we need to explain how symmetries act on it. So part of the so we take an anti-symmetric binary operation, and we impose one relation, the Jacobi identity. So you take elements of the free operad generated by this single element will be all possible binary trees with labeled leaves up to equivalences telling that at each vertex you can swap the left and the right subtree and multiply everything by -1. And then you take this element, the sum of these three trees in the free operad, and mod out the operatic ideal generated by it, or in more down-to-earth terms, you mod out all possible consequences of the Jacobi identity obtained by pre-composing or post-composing it with something. Right. So this is a very nice operad. Suppose that we would like to degenerate it into an operad with monomial relations. Suppose that we know how to as I told you earlier, what happens for algebras, if you take an algebra represented by generators and relations and just retain the leading terms of relations, then the quotient might be bigger than needed. And so, in fact, we need to extend our system of relations to get the correct size, but it is always possible. What happens here is very disappointing. Suppose that we know how to order monomials, how to pick the leading monomials out of these leading monomial out of these three. Well, let's say, for instance, that we picked this one, which is not particularly important because, as you see, these monomials are in the same orbit of the symmetric group. So I need to make a choice now. Let me choose the first one. Let's, instead of imposing the Jacobi identity, impose this relation given by this supposed leading monomial of our relation. But, well, since we have symmetries acting everywhere, if this guy is equal to 0, then each of the other guys is also equal to 0. So the monomial, suspected monomial degeneration of our operad is not bigger. It's almost completely vanishing, because this relation implies that all possible trees with at least 3 leaves completely vanish. So we have a little disaster, really, and it is not possible. It's not quite clear what to do with that, because symmetries are here. So in addition to precomposing and postcomposing, we have those consequences of identities which are obtained by symmetric group action, and this is not particularly good. Moreover, in the corresponding component of the free operad with one binary generator, this element, the Jacobi identity, is the only one-dimensional subspace invariant under symmetric group. So the only thing you could do to find a monomial degeneration of this relation is to just retain this relation. You cannot really do anything else. Right. Now that, so my point is that we should not be discouraged by that, and somehow find a better working space to pursue the same philosophy of retaining leading monomials and so on. But the most important point is that for these purposes, symmetries are spectacularly bad. So the first thing to do is to move away from the category of symmetric collections. And so the plan is that let's go to the category of non-symmetric collections, which with this monoidal structure I wrote previously is not really helpful for our purposes. Maybe let me say one word why it is not particularly helpful. If you have a symmetric operad, you can, of course, just forget about symmetries and regard the non-symmetric operad. Well, this operad Lie, as a symmetric operad, it has this very nice structure. It is generated by one binary operation, and it has some non-trivial identity for this operation, and so it has some rich structure. If you just forget about symmetries naively and regard the operad Lie as a non-symmetric operad, this operad will become a free operad on infinitely many generators. So it has entirely different flavor and qualities to it, and it's not a particularly helpful replacement. So what I shall do now, I shall define a different monoidal structure on the category of non-symmetric collections, which I shall call shuffle composition. So I'll take the liberty to just adapt this formula already written here. So I denote this circle with the subscript SH for shuffle, and instead of asking my surjection from I to integers from 1 to k to be non-decreasing, I will relax that condition and ask that the smallest elements in the pre-images of integers from 1 to k are in the increasing order. at least this condition, well, I'm allowed to write it since on that half of the blackboard I'm dealing with finite ordered sets, so I can compare things. Now let me explain, let me formulate a result which shows why this definition actually has a chance to be helpful. So there is a forgetful functor from ordered sets to finite sets, and therefore the forgetful functor from symmetric collections to non-symmetric collections. So I denote it by subscript capital F. So I goes to IF if I is an ordered set. IF is the same set without the order. We forget about the order. And then of course, so functors go in the opposite direction. So I have this forgetful functor from symmetric collections to non-symmetric collections. Well, if you recall that to define a symmetric collection, you basically need to have a collection of representations of symmetric groups, and to define a non-symmetric collection, you just need a collection of vector spaces. You just forget about all the symmetric group actions. And that's what happens here. And I claim that if we consider these two monoidal structures, symmetric collections with the usual composition and non-symmetric collections with shuffle composition, then the forgetful functor is monoidal. So you take two symmetric collections P and Q, compute their symmetric composition P circle Q, and forget about symmetries. You can either the other way around, forget about symmetries right away and compute the shuffle compositions. Those two are isomorphic as non-symmetric collections. Maybe since when I was a PhD student, everyone was teaching me that every talk should contain at least one proof. So let me prove this statement for you. It is very straightforward and pleasant. So what is the difference? What is the difference between these two formulas on the left and on the right? Here we have the symmetric group, and we have all possible surjections. Here we make the symmetric group go away and impose some restrictions on our surjections. So how to understand that these two are intimately related? Well, in fact, on the left, this direct sum over all surjections of k-fold tensor products is a free module over the symmetric group. And this restriction on the surjection is just some choice of generators of that free module. That more or less completes the proof. So as I said, the proof is very nice and short and pleasant. But however nice and short and almost empty it looks, it has some lovely consequences to it. Namely, let me start formulating consequences, and then we discuss some examples. So suppose that X is a symmetric collection then we can take the free operad generated by X, which will be a symmetric operad. And then we can forget about its symmetries. Or we can forget about symmetries of X right away, view it as a non-symmetric collection then, and build the free shuffle operad. These two are isomorphic as shuffle operads, as monoids in the respective monoidal category. Furthermore, suppose that we take the free symmetric operad generated by X and take its subcollection R. Then we can form the corresponding operad defined by generators and relations, the operad with generators X and relation R. So similarly to what we were doing in the Lie case. So in the Lie case, X was a collection of those one-dimensional subspaces of binary operations for each skew-symmetric binary operations, and then R was the linear span of the Jacobi identity. So we can build this operad, and we can forget about its symmetries. Or we can forget about the symmetries of X. We can build the free shuffle operad. We already know that there is this identification in the previous line, so we can view RF as a subcollection of the corresponding guy, and mod out the operatic ideal generated by RF. Then these are also isomorphic as shuffle operads. This is already a very important point. As I told you, if you regard the operad Lie as a non-symmetric operad, it becomes a free operad with infinitely many generators. So the set of generators changes, the set of relations changes. If we regard it as a shuffle operad, this statement tells us that it's an operad with the set of generators of the same size as a vector space and the set of relations of the same size. So it is much closer to what we had before. And furthermore, maybe before I move to some concrete examples, let me make a statement explaining the relevance for the not yet discussed in detail causal duality for operads and things like that. Since we regard operads as associative algebras, and for associative algebras, you can do various homologically or homotopically flavored things. So you can build the bar complex, you can compute the Quillen homology in the appropriate model category, and so on. So, for example, so you can build the bar complex, so P is symmetric operad. You can build its bar complex, which will be a differential graded co-operad. And you can forget about symmetries. Or you can regard your operad P as a shuffle operad, build the bar complex in the appropriate category, and look at that. And then these are isomorphic as differential graded shuffle co-operads. So at this stage, the moral of the story is that if you have if you have some question about symmetric operads that you can formulate without explicitly referring to symmetries, then you can move to the shuffle world, solve it there, and be quite happy, because you can, from that you can actually recover some information in the symmetric category. And if you need some information about symmetries, the situation is a bit more subtle, and I definitely won't be able to discuss it now. But for example, if you want to prove, if you want to construct build the minimal model of your operad, and in particular you want to prove that your operad is causal, so some standard minimal model would work, it is one of the equivalent definitions of causalness says that the bar complex of your operad has its homology concentrated on the diagonal. In other words, the off-diagonal homology of the bar complex is equal to 0. 0 with or without symmetries is 0. So this is a very good instance of a question that you can formulate it without referring to symmetries. And so you can actually, to prove that an operad is causal, you can do it in the shuffle category instead. And for that, there are various methods, because essentially one result which implies causalness is existence of a quadratic Grobner basis, and that is somehow what you can efficiently check. And so for various operads for which the corresponding result was proved by, over the last 15-something years, by a collection of beautiful tricks, borderline black magic, you can just prove it in a very easy and straightforward way, doing a short, nice computation. Now, let me, in the remaining time, give you a couple of examples, because that was a bit abstract, and my secret goal is to enable you to easily solve Bruno's exercises for his course. So let me show how all these things work, how you actually. Let's start with our favorite operad, with the operad of Lie algebras, and apply the forgetful functor to it and see what happens. Well, for the diamond, I shall refer to the respective page of your beautiful book. But
Are you going to write a shorter book then?
Yeah. So we had this Jacobi identity. Let me remark here on the right side of the blackboard that that formula for shuffle composition that I wrote, if you view it in the language of these two-level tree compositions, means that now the trees that you allow are planar trees whose leaves are labeled by elements of your finite ordered set, and there is a condition on how you can label these guys on top. Namely, so there are those sort of clusters of things corresponding to each of the places where you inserted operations from Q. So there should be, let me give you maybe an example. So in each, first of all, in each of these clusters, labels should increase from left to right, and also minimal elements of the clusters should increase from left to right. So there is no problem between these 3 and 2 because they're in different groups of variables, essentially. Now let me, when you build the free operad, you can, the free symmetric operad, you consider all possible trees whose internal vertices are labeled by your generating operations and leaves are labeled by elements of your set. But then, if you are dealing with symmetric operads, you can permute things. You can act by the symmetric group on all the internal vertices, permuting its inputs. And as I said, the idea of that isomorphism, idea that's saying that, of proving that forgetful functor is monoidal, that using the symmetric group, you can actually order the inputs in any way you want. And what we want is to order them so that those inputs are ordered in that way according to minimal elements, so the minimal leaves of the corresponding subtrees increase from left to right. Let me be a bit more specific. For this particular example, let me apply the forgetful functor to the Jacobi identity, because so far these guys don't look like these guys. So this is all right, this 1, 2, 3. With this tree, I will apply this local symmetry at the bottom internal vertex. So I keep this 1, 2, 3. Then remembering that my operation is skew-symmetric, replace this guy by 1, 2, 3. And again, remembering the skew-symmetry, write minus 1, 3, 2. And here you have an example of the same sort. So, of course, this 3 is to the left from this 2, but this 3 is not the minimal element of anything, so we don't care about the relative order between 3 and 2. The conditions that we should check are a local condition at each internal vertex. So we look at this internal vertex, and we see, then we see 1 and 3, and they indeed increase from left to right. We look at this internal vertex, and we see the minimal element 1 here, the minimal element 2 here, and they also increase from left to right. And these are the only conditions you should be checking.
Is this exactly the Chan-Linden-Fox basis?
Well, so far, I haven't given a basis for, but it's close to that. I mean, since we're talking in the operatic language, we shall obtain bases for multilinear components of freely algebras, but it is close, but it depends on the choices that you make. So at least now, this rewriting allows us to view these guys as elements in the free shuffle operad, because once we forgot about the symmetries, our free, so here we had this free operad modulo Jacobi identity. Now, we don't have symmetries anymore, so I have the symbol 1, 2. I do not have symbol 2, 1 at all. I build the free shuffle operad from it, so these 3 guys actually live in the free shuffle operad generated by that symbol using iterated compositions of that sort. And I mod out this guy, which let me call J, and this is the Lie operad to which we applied the forgetful functor. Now, there are some things which I don't have time to explain. To proceed with my plan, to proceed with passing from an operad to its degeneration with monomial relations and so on, I need to define a good ordering on monomials. Basically, an ordering that we need is an ordering which is compatible with all possible compositions. Compatible in the sense that when you compose several things and increase at least one of them, the result increases. So your ordering should, for your ordering, the composition of several elements should be an increasing function in each argument. And I don't have time to define ordering, but I suggest for now, I suggest to you to believe me that first of all, such an ordering exists. Second of all, in this case, when we just have one binary generator, in fact, it is possible to pick an ordering to make each of these guys the most important one, the leading monomial. If you take an ordering for which this guy, 1, 2, 3, is the leading monomial, you will get, and consider the corresponding shuffle operad. So now I want to emphasize, when we say that this guy is equal to 0, it does not imply any longer than that other guys are equal to 0, because symmetric groups don't act anymore. That's a very important, the most important feature of this construction. There is that wonderful metaphor due to Sergei Merkulov comparing an operad to the smile of a Cheshire cat, saying that so we start with an algebra, we look at all operations that can act in that algebra, and then the algebra, similarly to what happened to the Cheshire cat, disappears, and what remains just the collection of all operations that act on it. That, yes, and in a sense, so moving to shuffle operad, I guess within the same metaphor, corresponds to saying that the Cheshire cat and its reflection through the looking glass are two entirely different characters. We do not draw any relationship between them anymore. But anyway, so if you impose this relation, then it turns out that you don't really need to impose any further relations to get an operad which is of the same size as the operad Lie, and the basis for the components of the operad Lie that you get is indeed very, very close to Linden, Sheshov, and others. Not quite it, but very close. If you, however, take this guy as the leading monomial, you actually get something even much more tractable, because this tree, so this tree that appear in the Jacobi, these three trees appearing in this shuffle version of the Jacobi identity are the only three elements of arity, three in the free shuffle operad. So. And you can see that this guy, 1, 2, 3, it's the only tree which is growing to the right. And if you use, well, the most naive and obvious notion of divisibility of these three monomials, which I haven't explained to you precisely, but it is if you spend 30 seconds thinking about it, you will easily figure out what it is. Then you will figure out that trees which are not divisible by this guy are just all trees growing to the left. So, and all shuffle trees. So you will need to have one here because of this condition of increasing from left to right. And for other elements, all other elements are for all other vertices, the smallest element on the left will always be 1, so there'll be no other restrictions. So all possible shuffle trees that you get are trees of this shape, which instantly shows in particular that the dimension of the nth component of the operad Lie is equal to n minus 1 factorial, and a basis can be chosen using these left-normed commutators, which is a very nice result. Let me just use 2 more minutes. I still have, I think, 2 more minutes. Yes, very good, very helpful. And tell you briefly what happens, what you should do when you start with an operad of associative algebras viewed as symmetric operad. Because in the associative case, if we view it as a symmetric operad, in principle, from the very beginning, we have these 2 elements, 1, 2 and 2, 1, which are both perfectly legitimate. And I just told you that I only allow trees where things increase from left to right. So these are kind of illegal immigrants in the shuffle world. The trick here is very simple. You should just introduce a new element, 1, 2 with a bullet here, which denotes this 2, 1. And then, for example, when you have the
Sorry, so before that, in the Lie case, it appeared as if you had 3 possibilities how to order monomials so that one of those 3 would be the top one.
Yes.
And you gave 2 descriptions
Yes.
of what you would get.
Yes.
So what you get in the third.
In the third, it is very similar to this one. So for the 2 guys which grow to the left, the combinatorics of allowed trees is somewhat similar, and here you see some drastic difference. But for example, this associativity relation 2, 3, and 1 is equal to 2, 3, 1 in the shuffle world will become this one.
So you kind of introduce second equation?
Well, I just named the product 2, 1 by this bullet. So now I just
So sorry, so it has 3 is not a shuffle tree. No, the right combo is 2, 3, 1. It should be 2, 1.
well, no. So this guy lives in the symmetric world, and this is the result of applying the forgetful functor to it, translating it into the shuffle world. Because here I had the problem with the local ordering at this vertex, so I had to swap things and put here 1 and 2, 3. And here I had local problems at each of the vertices because there were contradictions with minimal elements. So I had to swap at both places. So, and finally, it turns out that in this associative case, there is an ordering of monomials for which the leading terms of our relations will be precisely the following. So there are 6 relations. The space of relations and the symmetric group is a regular representation. Let me write down the 6 leading terms. There will be 4 leading terms which are all trees growing to the right, and two trees like that, where they grow to the left. Both possible orderings here are allowed. The root vertex is bullet, and the other vertex is the normal vertex. And the trees which are allowed, the trees which are not divisible by these 6 monomials, are precisely trees growing to the right, where you have some normal vertices from the root to somewhere, and then you have several bullet vertices on top of them. And the number of elements like that is equal to n-1 factorial, because you have all permutations of leaves here, times n, because you have here n-1 guys. Some first few of them will be normal vertices and others will be bullets. So there are n possible things to do that. You can have 0 bullets, 1 bullet, and so on, n-1 bullets. So the familiar fact that the dimension of the multilinear component of the symmetric associative operad is equal to n factorial, because if you have an associative product, there are n factorial ways you can multiply n elements. In this case, you have this kind of peculiar basis where n factorial is equal to n-1 factorial times n in this strange way. And this basis actually can be used to answer some questions about associative operad. It's not entirely random and entirely pointless, but finally, the very last thing I want to say is that in both of these cases, we actually were very lucky, in the sense that we started with some defining relations, we took their leading terms, and the corresponding monomial degeneration was exactly of the same size. As I said, in general, you should expect that the monomial degeneration would be bigger, and you would need to perform that computation based on diamond lemma to extend your set of relations to a slightly bigger and slightly better set of relations, of which the leading terms will give you the monomial degeneration of the correct size. Okay, I'll stop here.
Thank you. Is there any question, remark?
When you pick up an order on the street, you act as it was two different operations, one is bullet and one
Yes.
the same. So you actually introducing this operation.
Well, I mean,
Which comes from this.
these operations have to be introduced at the earliest stage, when we actually specifically apply the forgetful functor to move to the shuffle world, and then in the free shuffle operads, those operations are regarded as completely unrelated, and you just introduce some ordering of monomials. You don't need to remember anything about symmetries anymore.
It reminds me of something that was Jean-Louis Laudet, who was saying, one can build antagons, but in fact it should be not a sociahedra, but a permutahedra, is the real understanding of the thing. And I was wondering whether this could not be understood.
Yes, it can be understood. If you look at the paper of Jean-Louis and Maria Ronco called Permutads, you will see precisely how it should be, the pentagon-related computation should be understood in this framework. The permutads are special kinds of shuffle operads as defined here, and this perfectly fits into this framework. Yes.
Well, what about Leibniz algebra? Do they fit in that?
Yes, Leibniz algebras have, as shuffle operads have a quadratic on the basis, you can obtain nice bases in the multilinear components, prove casualness, everything instantly works.
Can I make one comment to emphasize that? You didn't explain the relationship with the diamond lemma, but you extended the diamond lemma in the context of this shuffle operad, which gives a very naive and stupid way to prove causality. You start from an ambiguity, you rewrite, And if it's confluent,
Yeah.
you're done.
I said that.
Is it-
I said that.
I tend to emphasize it. And
Okay.
this is a really beautiful way to prove causality.
By diamond lemma?
Yes,
Yeah, okay.
yes,
Yeah.
it's really beautiful. I just wanted to say it's beautiful.
Thank you.
Any more questions? Let's go to eat. Okay, so thank Vladimir again.